Imagine you are at a garage waiting for an engineer to fit a new tyre on your car. The receptionist tells you that the expected waiting time is 10 minutes, so you find a seat and start waiting. After waiting 15 minutes, you go back to the desk and ask for an update. The receptionist informs you that your expected waiting time is still 10 minutes. Confused, you say, "This can't be right. Surely the expected waiting time should have gone down." The receptionist tells you that the time it takes to fit a tyre in this garage is an exponentially distributed random variable. So why does this matter? Well, the exponential distribution is memoryless. We'll see why this is the case with a simple geometric argument. But first, let's review the mathematical definition. The definition says that, conditional on having already waited time t1 without the event occurring, the probability of waiting at least another t2 units of time for the event is equal to the unconditional probability of waiting at least t2 units of time. That's quite a dense statement. The key idea is that for memoryless distributions, the conditional distribution is the same as the unconditional distribution. Let's visualize this geometrically. Start with an exponential distribution that describes waiting times. Condition on the event occurring after at least t1 seconds, producing a new probability distribution truncated at t1. Notice that the probability of waiting an additional t2 seconds or more is the same as the probability of waiting t2 seconds or more according to the unconditional distribution. The examples so far have considered the case where we are waiting for a service to finish. But what if we find ourselves in a queue? Let's say that you join a queue third in line at a supermarket. The amount of time you must wait for service is equal to the sum of two exponential random variables. These come from the service times associated with the other two customers in front of you. Conveniently, the sum of exponentially distributed random variables with a constant rate follows a gamma distribution. In this scenario, is the distribution of waiting times still memoryless? Let's recreate the geometric argument for the gamma distribution to check. Start with the gamma distribution that describes waiting times. Condition on the event occurring after at least t1 seconds, producing a new probability distribution truncated at t1. The probability of waiting an additional t2 or more seconds is not the same as the probability of waiting t2 or more seconds according to the unconditional distribution. Let's look at the actual probabilities. If you have already waited for 1 minute in the queue, the probability that you need to wait at least another 1.5 minutes for service is 0.39. On the other hand, the probability of waiting at least 1.5 minutes for service right as you enter the queue is 0.56. The longer that you wait, the more people will be served, so the probability of an additional wait decreases. Memorylessness is all about the conditional distribution. The exponential distribution is the only continuous distribution with this property. The geometric distribution is the only discrete distribution with this property. The next time you are waiting, think about what your waiting time distribution might be, conditional on the time you have waited so far. Is it memoryless? I'd love to hear about any real-life examples you might have of memorylessness. Let me know in the comments.